Hi, everybody. My name is Chamiel. I'm a director of algorithm engineering at Taboola, and I would like to talk about how we approached the problem of content recommendations using deep learning. More specifically, I'll try to convey the message that it's a good approach, and then we're going to dive in a little bit to get a bit of a taste of what can we do with deep learning, specifically about language modeling. So, Taboola. We are the guys that appear under the article usually with content recommendations. Usually they come in two flavors. One is links within the publisher or within the website where you're browsing in. And other recommendations come from other websites. And these are sponsored recommendations to many other websites across the web. So we are quite a big operation. The numbers are growing. So we see many users across the internet. In the US, our reach is quite high, so it means that we see, I think the numbers are, we see a US user, we see them twice a day, something like that, on average. There's a lot of data going through the pipes. I think this slide is here, mainly because later on we'll come back to the question of the size of the data and what can you do in terms of modeling using your own data. So that's mainly why the slide is here. Also, in terms of performance of whatever engineering you got to do in order for your models to actually return on time, it's actually also very much influenced by the amount of data. 2 billion times a day, a user will go and ask for recommendations. You got to have it working pretty efficiently. So, but today, more specifically, the outline is we're going to talk about the problem setup. So, discuss what are we trying to solve here and some traditional approaches, which are great, but they have some drawbacks. And then talk about why really we want to employ deep learning here. Why the hell do we want to do this to ourselves? And a little bit of how we do that. And then we'll dive into, more specifically into language modeling and see what we can do there with deep learning. So what's the problem? 2 billion times a day, a user opens up a web page, and there's a little bit of JavaScript that sends a request to our servers and returns recommendations. What do we know at that time? We know stuff about the user, what they did in the past, so we track them across the internet, across their activity, and we know stuff about what they're doing right now, so what article they are looking at right now and where they come from in the world and some other things. And then we have to consult with some inventory of, let's say, around 1 million possible recommendations and come up with 3 or 6, something like that. So that's the challenge. And really, what's going to happen, the user is going to see this a widget, which is an image and a little bit of text. And that's really crucial for the problem because that's really what they see. They don't know what the article is going to be. They know that thumbnail, that's the image, and a title. So we're going to see what we can do with that. So what's the problem? We're going to try to rank the recommendations by some function of the click-through rate. That's the probability for a user to click. And a cost per click, the advertiser pay per click. And some other metrics which are more specific to every advertiser that happen after the click. The click-through rate, we don't know. That's what we need to estimate. So that's what we're going to talk about today. Okay, that's a difficult thing to do, and why? So, as opposed to, there's a few unique things in content recommendations and recommended systems actually in general, as opposed to other machine learning problems. So, first of all, the feedback that we get from the users is completely implicit. The most explicit thing we know about the user is when they click on a recommendation. That's when they tell us, okay, we like that. Okay, that's we don't know for sure if they like that particular article or they like the type of that content. We know something about the click. It tells us some positive reaction. It gets much more complicated when we look at what they saw and didn't click. So maybe they didn't see the recommendation really, even if it was visible to them. Maybe they didn't focus on that at that second. Maybe they liked some other recommendation which was next to it. So it's complicated. Secondly, the data is very sparse. So we track users across the internet. For every particular user, for some of them you have a lot of data. For most of them you have a little bit. So we need to work with a click or two in the past, stuff like that, and that's a difficult thing to do. Another thing which is also unique to this problem is that we don't really have a human baseline. So for a lot of machine learning problems, especially problems that people tackle with deep learning, you can show humans the problem, and they can tell you whether the algorithm did a good job or not. So in image recognition, for instance, let's say that I'm building a classifier that tries to recognize whether there is a dog in the image. I can show it to people, and they will tell me if there is a dog or not. There's not going to be much argument about that. In Taboola, it's not the case. There's just too many options for the human to know what's going on. For instance, look at the title here at the bottom. Walmart cameras capture these awesome photos. Can you tell me if that's going to be better or worse than changing the word to hilarious photos? Well, we can guess. But really, it's a difficult thing for a human to know, so we need to let the data speak to itself. Later on, we'll come back to that question, and we're actually going to answer that question later. Similarly, okay, completely different content. So that one's talking about some funny photos from Walmart. The second one is talking about some photos from World War II. Different users, we react to them differently, so it's complicated, basically. And also, our world is constantly changing, so the internet is changing every day, more or less. There's new news, that's why they call them news. Also, the advertisers keep on changing the stuff that they want to recommend to our system. And that's also quite it's making the problem much more difficult. Okay, so let's have a look. So I hope that we're convinced that it's a difficult problem to solve, and a tough life for me. So what are the traditional approaches? How do you start? So the most natural way of thinking about so the problem we're trying to solve is to estimate the probability for a click. What is going to be the click-through rate, the CTR? So a lot of people approach this as a classification problem, where the classes are click or not click, and solve it with logistic regression. So that's an obvious choice, and you're probably doing a lot wrong if you didn't start with that. So we can take the features, and you chuck them into a logistic regression model, and you classify it, and you fit it for a click, non-click. You're probably going to have to do something with your data in order for it not to be skewed to the non-clicks, because there are many more non-clicks than clicks, but that's mainly what you need to do. And then you assume that the model it's a linear model, but there are really non-linear things that you're trying to do in the very core of the problem. Basically, we're trying to find what are going to be the relation between users or context and recommendations. So that's a linear model not going to do that. It's only going to find which users are more likely to be clicked, or which items are more likely to be clicked in general, but not for a specific user. So you can break that nonlinearity by doing a cross product. So you can do a cross product of a user feature and a recommendation feature, and then by that you introduce nonlinearity into your model. That's a pretty simple thing to do. Also, there are other things which are nonlinear. For instance, you could have a numerical feature, let's say the number of clicks, and maybe it's not linear. So you can bucket it and introduce nonlinearity like that. And then slowly you start going to introduce all sorts of things into your model which really fiddle with it. We call it the bag of tricks. Think about it that when you solve the problem, when you do the cross product that we discussed, taking user features and item features, you introduce features which are could be very, very sparse and with very, very high dimensionality. So you're going to have to do something about that. Usually linear models don't like that so much. So you can do the hashing trick or whatever. It's starting to be complicated. Moreover, remember that at the end of the day, the users see images and they read text. So they read the text, which is the title of the recommendation, and also read the text in articles. And that's also very useful information, their browsing behavior. So you want to learn you want to create some generalization from this. You want to know which text is most successful and which images are most successful for click-through rate. Okay, so you can do some name entity extraction and chuck the name entities as features. And you can send your image to an API server or do it yourself that does object recognition and chuck that into the model. And then you're getting into this clutter of different algorithms, different systems that are supposed to interact with each other. And it's not so much fun. I mean, it's good to start with, but at some point it becomes a bit of a headache, and it's not very proficient either. Okay, but that's a good start. Another concept, which tackles the recommendation problem more directly, is called matrix factorization. So here, we have a matrix, let's say, of users from one side and items. And for some of those entries, we have information. So we tried item 1 with user 1, and we know what is the click-through rate. And matrix factorization aims to fill up that matrix. So it's actually looking at the problem of matching content with users or content with other content much more directly. It's really designed to find a relation between two things, as opposed to logistic regression, which is not designed for that. Okay, so that's great. So the idea is you can fill up those gaps, and the way you do it is by these optimization algorithms that do that. But basically, every user will get some sort of a vector representation, and then the dot product, and every item will get a vector representation, and the dot product of them will be the value, will be the estimation. So the way it works is that the users which are more similar to each other, even though they have not a lot of data, they will borrow strength from each other. So if I have let's say that I recommended some item on users which I saw them a lot in a news website, let's say like USA Today. And now I have users which I see a lot in another news website, let's say it's similar, let's say NBC News, something like that, where I don't have a lot of data. So this model will allow us to borrow strength from one point to another, so that's attractive. However, it's a bit of a lie because it doesn't come very naturally to probabilities. Matrix factorization was designed for recommender systems where the response is in star rating, 1 to 5. So you can do something ones and zeros. You can do all sorts of tricks for that. Also, it's not really designed for multiple dimensions. You can look at the user and item dimension and the context item dimension, but then what? You want to combine them and get a final estimation. Okay, so drawbacks here. So that's what brings us to looking at the problem with neural networks, actually even before we go into deep learning. So neural networks, we'll see in the next slide, that will give us a really elegant mix of matrix factorization, finding relation between stuff, and classification. And also it has many other, and then it opens us to a new world of options, specifically language modeling and image classification. We can do really high-end stuff. So let's have a look at that. So let's have a look at the basic. How am I going to frame this problem now with a neural network? So very simply, this is a matrix factorization solution for using a neural network for finding relations between items and between contexts. So I'm using embeddings. It's not a word embedding, it's embedding of a different entity of items and users, let's say. And the way it works is I fit my network with items and users, and where I know the CTR, I know whether there was a click or not. And then I create this vector representation of items, a vector representation of users, where the dot product of them will be correlated very highly with CTR. So usually when the dot product will be high, CTR will be high, and the other way around. So that's already really cool, because look at what we did. We took we framed a classification problem with matrix factorization at the same time. So we took the good from both worlds, and it's really, really nice. However, if you remember in the beginning, we discussed how the world keeps on changing, meaning it's going to be a lot of new items all the time. It's called the cold start problem. So advertisers add new campaigns into our system, and we need to know right away how they perform. If we wait too long, they're just going to leave us and go somewhere else. And so we're going to create, so here, it means that for if I'm using the item embedding on the items themselves, I need to know a lot about the item. I need to see the item many times and many responses from many users in order for the embedding to be good. So you need to introduce some features under that. So we actually we can look at some features. We call these things subnets. And you'll see that the more I progress with the talk, the more I'll talk about those subnets, or parts of the system which are designed to solve part of the problem. Here, for instance, this is going to be a model. We'll have a look at an example in a second that models the recommendation, the title and thumbnail. And it's going to look at the words and the image itself. So if I get a new item into the system, right away, if I've seen the words in the title and I've seen similar image before, then I will be able to say what's going to be the click-through rate right away. Similar thing with the users and the context, and then we can start building our problem according to the business problem, really, according to the optimization problem directly. So let's have a look at dive in a little bit. So if you remember, we discussed, well, the fact that we show the users thumbnails and titles. So now what we can do when we have deep learning, we have this ability here to do whatever we want here. We can design a whole network there with whatever tools we want. So we can use the off-the-shelf tool that everybody uses in NLP for language modeling. We can use embeddings and LSTM. We will see an example in a second. Same thing with the image. We can train our models using techniques from image classification and tailor it for our specific problem. And what do I mean by that? Sometimes recommendations are great, not only because of the content of the image, but also because something else. For instance, look at the recommendation in the middle. It talks about an historical event. I think that when you look at it and you see that it's black and white and it's graded, it's graded a little bit, and you can quite quickly see that it talks about a historical event. That's the sort of a thing we would try to capture. Same thing here. Maybe, I don't know if you can see, but there are clouds in the sky. So maybe if there are more or less clouds, it's going to influence the click-through rate. And that's not something that an off-the-shelf image classification algorithm is going to give us. So we're going to be really going to train it ourselves and train it to our own problem. OK, so let's try and see an example from title modeling. So really, we're going to try and decompose this to the problem of modeling the title and modeling the thumbnail in particular. So we don't have time for the thumbnail, but we're going to talk about how we're going to model the text that the user sees as a title. So for instance, a very natural choice is to model the title as a, so we take the words in the title, we take every word, we can tokenize it, and then we create an embedding for every word. And we'll build an LSTM model on top of that. An LSTM model, if you're not familiar, designed to predict what's going to be the next thing in a sequence. So here, really, it's when you're trying to predict the next thing in the sequence, in terms of CTR, you can really find the patterns within the title. So phrases and stuff like that, things that work well in a title for click-through rate. Remember that we are building this where we're fitting it for our own problem. We're fitting it with clicks and non-clicks. So so we're going to create word embeddings here. And the word embeddings are not going to be necessarily things that are similar semantically. They're going to be things that are similar in their click-through rate, meaning that they work similarly, the performance is similar in a similar context or for similar users. And at the end, we'll get a title representation. So here, we took the problem, and we took a very specific sub-problem, and we can fit a model which tailors, which aims at that directly. OK, an example. I'm sure you're dying for an example. So this is well, we're using TensorFlow, and TensorFlow has got this amazing UI called TensorBoard, where you can plot things. A lot of people that do deep learning, well, one of the challenges doing deep learning is to understand what the hell is happening under the hood. So TensorBoard give you a really good start. You can look at the embeddings of stuff. So remember, we did word embedding, so we can just plot the nearest neighbors of a particular word. So here I took the word Messi. Messi is a football player who plays in Bnei Yehuda, I think. And so you can see there are a lot of other Bnei Yehuda. OK, sorry, Messi plays in Barcelona. So you can see really other, and he's also Brazilian. So you can see other Brazilian football players. You can see the word, sorry, Messi is Argentinian. What a mistake, wow. Sorry, Argentina fans. So, and you see the word Argentina somewhere and the word Barca somewhere. So the model, which was fit for CTR, was able to capture those things. Why? Because usually the same people interact with them. One thing that can really, really help, by the way, for fitting a language model for your own problem. So remember, the difference in this language model than a regular language model is that it's fit for click-through rate and not for the language itself. However, there's stuff that you can do to help you. So what think about it like that. In order to fit to understand what is the performance of a particular word, we need to see it many times. We need to show it to users and get the click-through rate. So there's a limited amount of information for that. However, as we go along, we accumulate titles, tens of millions of titles in our system. So what we did, we fit a model which is a word-to-vec model. A word-to-vec model is a model which aims to find what are the words in a context of another word. So find the word which is next to another word, or maybe the one after another word. So for that, you don't need the click-through rate at all. So you can fit a model, which is a pure language model, and then transfer it to your own problem. And that really helps with generalization. Another example, this is on a whole title. So we plotted the whole title, for instance, 15 rarely seen World War II photos. So we can see the really cute examples here. For instance, other things that talk about the military, other things that talk about photo galleries. So really cute things. Yeah. Okay, one last example. So another technique which is really common in NLP is using convolutional neural networks. The idea with convolutional neural networks is that you take your data and you chuck it into smaller parts in order to find patterns in the data. So our data is titles, and the small chunks are unigrams, like single words, pairs, triplets, unigrams, bigrams, and trigrams, and so on. So you can fit, I'm not going to get into the technical details of how exactly the convolutional neural network works, but just to give you an idea of what sort of a useful visualization you can do with that to really understand what happens when the user interacts with the title. So what we did, we plotted the activation of unigrams, bigrams, and trigrams on this graph. So the darker it is, the more influential it is for click-through rate. So the right column, it talks about the trigrams, which means Walmart cameras captured. That's the 3 words. And that was the most influential thing for click-through rate. That was the most influential thing that made user click on that, and when you have an estimation. Now, what happens if we change the word awesome to hilarious? Remember, that was the example we started with. We can see that all of a sudden, this area lights up. So the word hilarious seems to be much more influential to click-through rate than the word awesome. People like the word hilarious. Actually, they like the phrase, these hilarious photos, much better. The prediction went up, and we can understand why. So we can now go to an advertiser and tell them, if you have the word awesome, change it to hilarious, think your life is going to be, well, better. And also, if we try to change the word to the word funny, and all of a sudden it disappears. No one likes the word funny. People think probably it's boring. These funny photos sounds a bit juvenile. Maybe not a lot of people are going to click. And we're going to see why, and we're going to see the prediction went down. So that's a really useful thing that we can do with neural networks. Okay, so we can use the very, very high-end models like convolutional neural networks and create some visualizations that help us to understand what the hell is happening inside, or maybe even create products for that gives the advertiser some insight about their titles. So to sum up, we had this business problem of trying to fit a model for click-through rate using information about the user and the context and choosing from 1 million recommendations. And what we can do is build a graph that actually tackles this problem directly. We don't have any other moving parts. We don't have another algorithm that does image classification. It's all fitted within the same network. Now, engineering-wise, obviously, it's going to be difficult to predict using a very, very deep network like this. So you can decompose your problem. You can take out this area, for instance, the one about the image, and do the inference in separate, and save the result somewhere. But the idea that you fit your problem as end-to-end. You just fit the entire problem within a single network, and by that you get much better performance, much more tailored to the actual business problem. That's it. Any questions?